So, welcome back to everybody. We are in our regular lecture in the course of application of data science and AI number 2. I want to remind that this lecture is also streamed live today as a special occasion for an invited lecture that I will introduce very soon. And before starting with the invited lecture, I would like to make a recap of what we have seen this week. This week is the week where we did application in computer vision. We saw what is computer vision, several applications like image classification, image similarity search, and also how easy it is to do nowadays face detection, and how easy is also the blurring the face that we have. This is very important when we think about ethical points in AI and machine learning. And this brings us properly in the topic of the guest lecture of today. We will have here an invited speaker, Francesco, my personal friend. We know each other since many years, and he will give us this beautiful journey into the world of medical imaging, which is, of course, computer vision, but is applied to such a specific domain that you will see how much in-depth knowledge you need to have in both machine learning, computer science, and medical topics. Let me properly introduce Francesco, and after my introduction, I will leave the floor to him that will tell us a lot about this field. So, welcome, Francesco. Francesco is Associate Professor in Computational Pathology and Research Group Leader at the Department of Pathology at Radboud University Medical Center in Nijmegen in Netherlands. His main research focus is artificial intelligence for precision oncology in the area of pathology, with application to discovery and implementation of predictive and prognostic biomarkers in immuno-oncology, and computer-aided diagnosis for large-scale digital pathology and multimodal data. As a guest lecturer at Radboud University, he has been the creator, main teacher, and coordinator of the master course in Intelligent System for Medical Imaging. Please, Francesco, the floor is yours. I leave it all to you. We will all happy to listen this beautiful world of medical imaging.
All right, thank you. Can you hear me well?
Yes.
Okay, good. All right, yeah, good afternoon. Yeah, thanks for inviting me. Thanks for the very nice introduction. It's a pleasure for me being here today and have the opportunity to share some thoughts and to present some of the results of the research that I've been doing in my group. What I will present is mostly the work done by people in my group. I'm just here to present them. But to do so, I have to first share my screen. And I hope you can see. Can you see it well? Is that the right mode or presenter mode? Oh, that's the right one. Okay, let me just adjust these panels. Otherwise, these are all over the places. All right. Yeah, so we discussed with Pierluigi a bit the title of this presentation. We came up with the Cracking the Code as a catchy title. I think the content is mostly the impact of AI on medical image analysis. That's what I would like to talk about in the next, I think it will be 45, 50 minutes. Is that okay? Okay, please stop me if we run out of time. And I don't know how you guys do this, if it's more interactive or if you keep questions for the end. Both are fine with me. So
it's as you prefer. So
no, I have no preference. So
well, I think that if there is a burning question, maybe the students can ask you right away, and all the other questions by chat and also that come from the live stream from YouTube can be done at the end.
Yeah. Okay. Perfect. So let's get started. Well, first, these are my disclosures. And yeah, because as Piero introduced a bit, as you can imagine, I'm Italian. I know Pierluigi for many years, since the years we did our PhD together, actually in Spain, in Barcelona. But now I live in the Netherlands for many years, and I live in the city of Nijmegen. which is here on the map. You see it's like central east part of the Netherlands. It depends who you ask. Maybe it's more south. It depends. It's a bit of a controversial thing. And they claim it's the oldest city in the Netherlands, which is probably true, but don't tell people in Maastricht, because they also claim that Maastricht is the oldest city. So then you have to see. It's a very nice place. It's not that big, but it has 170,000 people. So actually fairly big if you, for also Dutch standard, let's say. It's crossed by the river, the Waal, which is like the final part of the Rhine. And actually, I checked, and there was something already before Christ, in the 12th before Christ, under the name of Novio-Magos. It was some kind of Roman establishment, let's say. So it is quite old. And it's also famous, maybe you have watched this movie, A Bridge Too Far. It's famous for some sad events that happened during the Second World War between Nijmegen and Arnhem, which is the next city. And it's also famous for an event that happens every year called the Vierdaagse. So it's 4 days, means 4 days in Dutch, where thousands of people gather together and they walk either 30, 40, or 50 kilometers a day for 4 days. And actually all the rest of people just party very hard all night long. And the ones that can still stand the last day, they also party quite hard, but otherwise they just walk a lot. And this attracts actually many people from all around the world and makes Nijmegen also famous for that. But so why I'm telling you this story? Well, to introduce that, in Nijmegen, you have Radboud University Medical Center, which is an academic hospital. It's the place where I work. It exists since 1965, and it has about 1,000 beds and about 10,000 employees. It's a pretty new building. I mean, they are renewing it very often. So this part that you see here in the picture looks very new because it's like 2 years old. It's an academic center, so you have, of course, patient care, but you also have a lot of research happening. And I put this picture because my kids are always find it very funny that it is so big that you actually need cars inside the hospital to carry patients from the main entrance to other departments. So they say, "Yeah, Dad, you work in a place, you have cars inside it." So they find it funny. Inside Radboud, which is academic hospital, as I said, there is a lot of research happening. And I'm part of the diagnostic image analysis group. This is our main website, diagnijmegen.nl. And it's a multidisciplinary and also cross-departmental group, which is partly in radiology, partly in pathology, radiotherapy, nuclear medicine, cardiology, neurology. And it's really a cross-departmental research group with mostly PhD candidates, but faculty members, postdocs, lab technicians, research software engineers. And we all work, pretty much all of us, most of us, we work full-time on research and development of artificial intelligence for the analysis of medical images. And myself, I'm in the pathology department, but I'm part of the diagnostic image analysis group, and our pathology part we call computational pathology group. So what do we do as DIAC? Well, we do medical image analysis, and we have always done it with machine learning, and in the last decade, essentially more and more with deep learning, and AI essentially is the umbrella term that covers all this discipline. So there are many applications in the medical field. You have images pretty much in very different departments and different diagnostic tasks. You can start with mammography. Probably you know about it. It's X-ray technology. You get a 2D image. Actually, you get some kind of 3D if you go to tomosynthesis, but this is what is mostly available for. It's used for breast cancer screening. So subjects, not patient yet, let's say, are invited to have regular screening, I think yearly or bi-yearly, after the age of 50, and they get a mammography. And if there is a suspicious lesion, then there is more investigation that is done. Still about X-ray, you can also have 3D images like computed tomography, CT, typically is done in the thorax, but you can actually have a full scan CT. It's done also, it's coming up a bit for screening programs to look for pulmonary nodules that could be indicators of lung cancer, but it's also done for, rib fractures and all sorts of medical investigation. It's not all, grayscale, black and white, boring images. There is also some colors in medical images. For example, you can have retina fundus images, like it's actually pictures of the back of your eye, like this one. And then it's used to diagnose diseases like diabetic retinopathy, for example. There was also a very popular challenge a few years ago on Kaggle about diabetic retinopathy. And then this is another colorful space. Digital pathology is the field of researcher I'm working with. And this also generates RGB images, but these are multi-resolution images. So you see here, sorry, can you see my mouse also? Yeah, okay. So you see here, this is a bit of a very high level representation of how the data is actually stored. It's organized in a pyramidal way with multiple magnifications. So this type of images really are huge, in the order of hundreds of thousands by hundreds of thousands pixels. And you really need specialized, APIs to really even view them, because it works a bit like Google Maps. So I will talk a lot about this modality because it's actually what I'm doing research on. But I will try to connect also a bit with, for example, radiology images with the CT. But maybe a bit more about pathology now. So where does this image come from? Back to our example of breast cancer screening. Let's say a patient subject gets mammography, there is a suspicious lesion, then they take a biopsy. And this is called a core needle biopsy. Essentially, they stick a needle in the breast, and then they get some tissue. This tissue is first fixed in formalin, and then it's embedded in paraffin. So it's it's a tissue block, it's wax, it's like a candle, right? But then there is tissue inside. And then in the pathology lab, they can cut it into stripes. Essentially, it's the tissue slides. And then these are very thin, between approximately 4 microns, the thickness. And then they stain it to give it some colors and see different structures. And then they put it in a glass slide. And then this glass slide, historically, the specialized physicians that are called pathologists, that are the ones that analyze the slide, they do it under the microscope. But nowadays, we can scan it with high resolution scanners, and we can get these type of images. So this is a digitalized slide of a breast cancer biopsy, pretty much the tissue that you have in this block. And you see this is pinkish and bluish, and this is because it was stained with hematoxylin and eosin. These are the names of the 2 components. And hematoxylin stains nuclei in blue, and eosin stains the rest of tissue in flavors of pink, let's say. And this is, as I said, it's really a lot of data. So this tiny fraction of tissue, which is about 1 millimeter thick and probably about a centimeter long, it's 3 to 5 minutes of an HD movie in terms of pixels. And if you go to the full tumor resection, it can actually be almost an entire movie or half a movie. So it's really a lot of pixels, a lot of data, which also gives a lot of opportunities for data analysis. So this is an example of a rectal carcinoma sample. So it was really resected from the patient, it's the full resection. And this is a whole-slide image viewer. So that's the name for digital pathology. We call it whole-slide images. And you see, it really works like Google Maps. You really can really zoom in up to the cellular level at very high resolution. So think that 1 pixel here is 0.25 microns. So you can really see these are all tumor cells. This is the connective tissue. These are probably a mixture of immune cells, stromal cells, etc. So you can really go to very high resolution and do a lot of analysis, even at cellular level. So it gives a lot of opportunities for computer analysis. So why do we do that? I showed a bit of an introduction. What is the reason why we have to do computer analysis on pathology images? Well, it turns out in the world, there is a shortage of pathologists. So the specialized medical doctors are mostly not present. You see the map is pretty much red. I mean, Western countries, North America is doing well. In Europe, I think we do overall well, Australia. But the big picture is that actually there is a severe lack of pathology. This is a study from February last year. So it's also very, very recent. So this is the first problem. The second thing is actually kind of good news, but we live in a future where there is aging population. So people live longer, right? Which is good, but it also means that more diseases come up and more cancers are found. So this actually depicts, I put all these things together. It's a clinical and societal landscape where we will have more cancer incidents. I talked about screening. So we will detect more cancers early so we can cure them, but there will be more tissue that is taken from patients. And then this means that there is more work for pathologists, but we have a lack of pathologists. And at the same time, the good news is that there is more and more availability of cancer treatments, which are actually very expensive, very toxic, and typically only work for a few subset of patients. So this depicts a picture where actually the costs of healthcare are going to grow. Actually, they are growing already. And at some point, it will become not sustainable anymore. So in the rest of this presentation, I would like to pitch a bit how we could use AI to reduce this healthcare cost and improve healthcare in general, focusing on reducing the pathology workup, so less work for pathologists, or a more efficient way to do diagnosis, and also how to address the cancer treatment question, how to best treat patients. Now we want to use AI, right? So then these days, when you talk about AI, you think about something like this, right? This is the Sora system of OpenAI. Probably you've seen that. I like this one. This is probably the video that I like best. This was generated by giving this text: photorealistic close-up video of two pirate ships battling each other as they sail inside a cup of coffee. And I like the cup of coffee very much because I play it again because I like it very much. I like, you see that the physics, also the dynamics of the fluid. I think it's really impressive how this system has generated this from scratch. I don't think it's overfitted on a video that you find on YouTube or something, because it's probably difficult to find these ships battling on a cup of coffee. So this is a bit the level of technology that we have these days. But actually, when it comes to clinical practice and still quite a lot of research, we still use this supervised learning. I understood this is what you have been studying also recently. So supervised learning, very briefly, it learns by examples. It doesn't use any fancy self-supervision techniques that is more and more popular these days. Supervised learning means that the truth is known. So the input data comes with labels. And these labels have to be usually made manually by experts. And you can imagine in the medical field, you need specialized experts to make these labels. So very briefly, you know how this works. Like, you can imagine a model as a gigantic mixer where you have all these knobs. Initially, it just produces noise, and then you start tuning these knobs by minimizing the prediction error. And this is the typical example with cats and dogs. So image classification, at some point you get it right. It means that you have trained your model, and your model is typically an artificial neural network. For images is convolutional neural network, where you have all these interconnections between artificial neurons, or the kernels of the convolutional layers. And at some point you have trained this model, right? And then you can apply to downstream tasks. And this is pretty much what I think in industry, what is mostly used for products, even in medical imaging. And also research is still relying a lot on this type of technology. We are also doing a lot of research on foundational models and multimodal models for medical applications, but this is still what is at the core of actually most of the applications that I will present today. But of course, we know that this is growing, right? So in the 50s, we have neural networks, and then we went to convolutional neural networks in the 80s with Jan LeCun and colleagues. And then we had recurrent neural networks with long short-term memory from Jürgen Schmidhuber in 1997 and his team. And then we entered the era of transformers in 2017, first with NLP, and then with vision transformer. And this is now, exploding, right? It's used in many different applications. And of course, you can say that this has happened and is happening because of a number of reasons, right? The presence of hardware advancements in GPU technology, some mathematical tricks that made back then also convolutional neural networks more trainable, more efficient. But I think the most important ingredient here is data, right? So having lots of data is really key. Without that, we are not in business, essentially. Of course, you can think about reasons where, models where you can also work in a low data regime. But I think this is the vast majority. In the vast majority of the application, data is really important. Not just the size, but the quality of the data. And especially when it comes to supervised learning, also the quality of the annotations. So let's say then we have the medical field, we have AI as a tool. We are curious about the performance of AI, right? And this is still an ongoing question. Like even this morning, there was a paper on Nature Medicine that was actually questioning the impact of AI in the field of radiology, if they were actually improving the performance and how this correlated with the age and the experience of radiologists, etc. But so historically, we have had a few moments where we have seen that AI could approach or even outperform human experts at some tasks. And I think the first example was AlphaGo. You probably know about that. Back in 2016, I think it became the world champion at the Chinese game of Go by defeating Lee Sedol, who was the world champion at the time. And then, of course, it was big news made by Google DeepMind. And then the news was that deep learning software probably was the first one that defeated human professional for the first time, right? Actually, it was for a game. and not yet in the medical domain. But we didn't have to wait too long, because a couple of months later, it came another paper, this time also from the Google team, on dermatology. And I think this was one of the first evidences in the medical field where AI could really perform at human level, or even better. So this was a paper about detecting cancer, skin cancer from RGB images, so pictures. And they did a comparison with a panel of dermatologists, so the medical specialists that check for skin lesions. And they had two studies with 25 and 22 dermatologists. And this is a bit counterintuitive, but these are ROC curves, or some form of ROC curve. So it's the plot of specificity and sensitivity. It goes from 0 to 1. And this means that when you are in the top right corner, you have the best performance. And you would have this diagonal that they don't depict here. That would be essentially like flipping a coin. So random guessing if it's cancer or not. And in principle, in ROC curves, I'm not sure if you have seen this before in your courses, but everything that is above this virtual diagonal that they don't depict here makes sense, right? Typically, you see this curve depicted like flipped left-right. So typically, you go to the top left corner as the top performance, because here actually the common one is sensitivity on the y-axis and 1 minus specificity on the x-axis, but doesn't matter. The message here is that you see the dermatologists are all these red dots. So these are the performance of their sensitivity, specificity. And the AI algorithm is actually better or on par compared to most of them. And this is for both studies. And actually, this was possible because the actual diagnosis of the skin cancer was not coming from the picture itself, what they used to train the model, but was coming from the pathology that was from the histology that confirmed the presence of cancer. So they took a biopsy or they removed the entire mole, and then they confirmed it was cancer. So actually, the algorithm was trained with a ground truth that was even stronger than the opinion of a dermatologist that could only see this RGB image. That's why AI could outperform these dermatologists. Because otherwise, we are in a regime that was the second paper a few months later. Again, the Google team, I think, in the area of ophthalmology, so retina image analysis. Here, they looked into diabetic retinopathy, and it's a similar story. These are ROC curves. This time are really flipped as I usually see them. So top left is the best performance, and the dots are, again, the medical specialist, right? But this curve now, it's on pair and approaches the humans. And this is because both algorithms, and the algorithm was trained with the opinion of ophthalmologists and not with, a stronger reference standard. So here, essentially, the best that the model can do is to stay within the inter-observer variability. So we had these two first evidence on ophthalmology and dermatology. So what about pathology? Actually, this is work that was done by my group. It was actually the time when I joined the group, so I was not directly involved myself in this study. This was on the detecting metastasis in sentinel lymph nodes so breast cancer metastasis in sentinel lymph nodes. Essentially, when they remove the tumor, before doing it, they inject a radioactive tracer, and then with the probe, they find when essentially this tracer reaches the first lymph nodes that are reached, they are also removed, because those are the most likely to contain breast cancer metastasis. And you can imagine that the metastasis can also be a bunch of tumor cells, and that's why this is a problem that essentially like finding a needle in a haystack, because so this is a section of a lymph node, and there is a tiny metastasis here. I don't know if you can see the purple dot here. It's just a bunch of tumor cells, but finding this metastasis can really change the way the patient is treated. So it's really important to do it, and it's very easy for pathologists to overlook it. So that's why we did this project, and actually this showed similar results. It's only a zoomed in part of the ROC curves. It's not the full plot, but again, similar story. The dots are the pathologist, and then the curves are the ROC curves of not one, but a bunch of deep learning algorithms. So this is a bit the background, right? The potential that has been shown by these studies, as well. All studies like 6-7 years ago, and in the meantime, more studies and more research has happened, which is what I would like to tell you about in the rest of this presentation, with a couple of examples in the space of radiology, taking CT as a use case, and then the rest will be all about pathology. So CT is a CT scan, so it's a 3D image. You can also see it as a collection of 2D images, like a stack of digital slides. So you can also apply your 2D convolutional neural network for image classification, for example. And one application that I've also worked on in the first year as I was at Radboud, actually I started as a postdoc in the radiology department, is to detect nodules. So you can imagine if you want to screen for lung cancer, first you have to find nodules. Probably most of them are benign, but some are cancer, right? So the first thing is to detect them. So how do you do that? Well, you need manual annotations of lesions like this. It's a solid lesion. And then you can have the typical trick of training a convolutional neural network to do patch classification, or if you have worked with object detection models like, I don't know, faster CNN or YOLO or these type of things, you can also use that type of models. Or you can also formulate it as a nodule segmentation problem, right? And then use UNet or any other segmentation module. But this would be the goal, say if it's a nodule or not. And then let's say it's a nodule, then radiologists are asked to check in this table. This is called LangRads guidelines. They have to check the type of nodule, how big it is, how does it look like? And then based on that, they decide on how to manage the patient, right? And then there is a number of options from just following up the patient in 12 months or 6 months, or do some more clinical investigation because it's suspicious for being lung cancer. And therefore, for doing this, you see they list a number of nodule types: calcified nodule, solid nodule, part-solid nodule, etc. So you need to not only detect it, but also classify it, right, to address this task in the clinic. So you can imagine doing exactly the same, right? You can do, instead of just detecting the nodule, you train a system to, given a nodule, to classify the class that it belongs to. So it becomes essentially a multi-class classification problem. So the use case here could be that AI could be a module that, if you do lung cancer screening and you have to find the nodule first, and second, you have to classify it to decide what to do with the patient, you could have something that automates this process or supports the radiologist in doing that. Because you can imagine there is, it's a tedious task finding all these nodules and then also classifying them. There is a high inter-observer variability. So having an AI algorithm that can help you there could be very useful. When you have to train the system and then you move back to the pathology space, you have to deal with these huge images, right? It's gigapixel images. And if you need manual annotations, well, I can tell you it's really a lot of work. You see, you may need very precise annotations of, this is a project that we did a few years ago, of the tumor region, the connective tissue, which is called the stroma, because you want to extract patches to then train your classification or segmentation or detection model. And here, you cannot do it yourself. I cannot do it myself. We really need the expertise of pathologists. And we need to really sit down next to them and discuss, okay, how would you make the annotations? What would you annotate? Then you take it, you train a model, you run it on a few cases, it doesn't work, you get feedback from the pathologist. So this really needs a multidisciplinary work. And actually, I'm happy that I can work in a hospital, because this makes this connection with clinicians much stronger and more efficient, because we have closer contacts with them. So let's say that then you have these annotations, you want to train your model, right? And then you want to do tumor versus non-tumor, or you can add other tissue types, but it's the same formula. You can use convolutional neural networks, for example. What do you want to use it for? So what are the applications? What are the problems? Well, it turns out, let's say, that there is breast cancer, right? This is our biopsy that we saw in the beginning. Then the next question is what type of breast cancer it is and how to treat this patient. Because it turns out that not all cancers are the same. So there is one characteristic of the cancer that is called, is the grade of the cancer, which tells a bit how aggressive it is. And over the years, there are several components that the guidelines have come up with, and pathologists have to score to essentially classify the grade of this cancer. And in breast cancer, there are 3 components. One is called tubular formation, and this is a visual example. On the left is a cancer that creates more tubules, so like these white holes, let's say, and on the right one is less. So you would say it has been seen that with more tubules, essentially, it's a higher grade, it's more aggressive. So pathologists have to really look at that, and they have to put the case into one of the 3 boxes, 1, 2, or 3, grade 1, 2, or 3, for the tubular formation. But I said there are 3 components. The second one is nuclear pleomorphism. And visually is something like this. This is 1, this is 2, this is 3. This encodes essentially how much tumor cells are different from healthy epithelial cells. So you see here on the left, these are more organized with an organized structure, and the more you go to the right, they become more chaotic, let's say. Of course, this is terminology and concepts that I learned by talking to my colleagues pathologists. I don't have a very strong medical knowledge to say that, but I know that in the guidelines you have also for this nuclear polymorphism, you have to put the case into 1, 2, or 3. And then there is a third component, which is mitotic count, and mitosis is one of the phases of proliferating cells, in this case is tumor cells. So they duplicate, and then at some point in this process, they have the mitotic phase, which makes tumor cells look a bit like this. So you see, they look different from these other ones. They are darker, they are more irregular in shape. And this is a characteristic that if you find a lot, it means that the tumor is growing fast, so it's more aggressive. So pathologists have to scan the slide, find they call the hotspot, so the region with the highest density of these mitotic figures, and in the hotspot, they have to count the mitosis. Depending on the number of mitosis, they have some thresholds, and then again, they put the case into a box 1, 2, or 3. So all these three things together form the grading of breast cancer as more or less aggressive. And you can imagine that this is important because these are survival curves of breast cancer patients with different grade. You see grade 1 cases do much better than grade 2 and 3 overall. So this is probability of survival over time. And actually, it's something that you have to do pretty right, because depending on this, you also make choices on how you treat the patient. And now we are in an era where there is plenty of options for treating patients, from immunotherapy, radiation therapy, targeted therapy, hormone therapy. And all of these choices are in principle possible, but you need to find which one works best for the patient. And grading is one of the ingredients to actually make this decision. So it's very important. But turns out that if you ask pathologists to do the grading, they don't agree. So this is an experiment that we did a couple of years ago. We took only one of these three components of grading, the pleomorphism, and we asked 10 pathologists from different countries in the world, and we asked them to score 125 cases. And this is the graph that we got. So every row is a pathologist and every column is a case. And the colors are score 1, 2, or 3 for green, yellow, and red. And you see, actually, there is a trend a bit, but they don't fully agree. And actually, it was pretty surprising for us to see that they completely agreed only on 10 cases out of 125, so only 8. Overall, they did agree mostly on cases, except a few outliers, like this one here said it was high grade, and the rest was saying it's low grade, and something maybe here the other way around. But this was really the first evidence for us for this task. There was not much also in the literature about pleomorphism, that there is quite some disagreement. And actually, you can imagine that this has some impact on how you handle the patient after that, especially when you also enter another layer of classification, which is not only about the grading, but also about the molecular component of the tumor. Because I told you that not all tumors are the same. If you start doing molecular analysis, and this is called molecular subtypes for breast cancer, you can further stratify these into different subgroups. And these subgroups, you see, also have different prognosis. And actually, so this is a bit of an old paper from 2003. At that time, this one, which is now called HER2 positive, was the one with the worst prognosis. Now there is a targeted therapy for this type of patient. So actually, this one is the worst one. Here it's called basal, but nowadays it's called triple negative breast cancer. And it's triple negative because essentially they do 3 molecular tests. And if they are all negative, then it's triple negative. So this is nowadays the most aggressive form of breast cancer. So not only the grading part based on morphology or whatever, also you have to look into the molecular subtype. So this triple negative is actually, as I said, pretty aggressive. And that's why, back to the example of our breast biopsy, the triple negative breast cancer patients are treated with chemotherapy as soon as possible. So right after the biopsy, before even they resect the tumor, they get chemotherapy. And this is called in the neoadjuvant setting. So neoadjuvant means before surgery, right? So in practice in the clinic, the triple negative patients, they pretty much all get chemotherapy. The problem is that only half of them actually gets some clinical benefit, which means that the other half are getting chemotherapy without any benefits. They get the toxicity of the drug, they postpone the surgery because eventually they do get surgery, but in the meantime, the tumor grows. So that's not really efficient. So it would be best to identify these patients and then just do surgery right away, or maybe do some other types of treatment. So this was a bit of a second part of background a bit, and now we are really entering the applications, how we can use AI with some examples of algorithms developed in my group in a digital pathology workflow, going from the very first step, which is scanning the slide, all the way down to treating the patient, right? And where we can actually plug in AI models that can help make the diagnosis more reproducible, more efficient, have better choices for better treatment selection for the patient, and overall also reduce the costs of healthcare. So let's start with scanning. So I showed you the glass slide, and then you put it in a scanner. You get a very high resolution gigapixel image. It turns out that you get these beautiful images, typically pink and blue, because this is the hematoxylin and neozyl staining that is done in the clinic regularly. But they have a lot of, several sources of potential artifacts, right? And here I just show a few of them. For example, you can have dust on the slide. You can have pen marker on the slide. The tissue can be folded because they lay down on the glass slide, and then it can fold a bit. There can be ink. I don't show it here, but while scanning, you can get regions that are out of focus. So this can all be a problem for a downstream AI algorithm because the predictions on tissue fold are pretty much unreliable. Same for dust and pen marker. But also for a pathologist, if they get a slide that is poor quality, they have to send it back. And that gets delays in the diagnostic procedure, more cost, more time, more waiting time for the patient, etc. So we said, okay, can we detect these artifacts as soon as possible? And actually, this is the output of a segmentation algorithm that we developed a couple of years ago. On this, this is a slide of a prostate cancer biopsy. So we developed this algorithm, and then we thought, okay, how can we use it? We want to use it as close as possible to the scanner, actually, right? So ideally, even running in the scanner, because as we scan, we want to check if the quality of the slide is good. Because if yes, then the slide goes to the pathologist, and maybe optionally with the support of an AI system. But if not, then actually the technician in the lab could work together with this AI system and decide what to do. For example, rescan the slide or clean it up and rescan it after cleaning. For example, if there is fingerprints or dust, etc. Or if really the tissue is compromised or broken, then they have to cut a new one, right? But if this all happens before it goes to the pathologist, we can improve the workflow, we can minimize delays, and we can improve the quality of the slide and therefore the diagnosis. So this would be a first example how we could use this technology to potentially improve the workflow in digital pathology. So then let's say the slide is good, right? We want to send it to the pathologist. And here the kind of provocative question is whether should we really send it to the pathologist or can we do something a bit different? And of course, the answer is yes, we need to send it to the pathologist because then they have to, do the final diagnosis and sign off the case. But it turns out that there are some applications where we can think about doing something a bit different. So for example, when we talk about the diagnosis of colon polyps and biopsies, so these are cases that come from population screening, what happens is that you have many cases, many polyps and many biopsies that, in that case, for example, in our hospital, we have 1,500 to 2,000 cases a year. So it's quite a lot. And it turns out that most of them are actually non-informative. So it's just benign lesions because it just turns out that during endoscopy, or maybe because of, the patients have some complaints or because of the, some suspicious results of the test during screening programs, then the patient gets endoscopy and then they get polyps. So the most polyps are actually benign, but still it's a lot of tissue and pathologists have to go over all this tissue and do their final diagnosis. So we thought, okay, can we have maybe a way to kind of pre-read or pre-screen these polyps and these biopsies before they get to the pathologist and maybe do something, maybe focus on the remaining 30% here, which is the clinically relevant because it contains some abnormality and potentially cancer. So we developed a ConvNet to essentially detect abnormal cases among all cases. And this is, again, the ROC curve of the system that we got. Actually, very recently, we are still working on the paper. And we got an area under the curve of 0.99, so it's pretty good. But that's not the interesting part. I think what is nice here, at least in this still lab-based setting, validation setting, is that we got 100% sensitivity at a decent false positive rate, about 45%. So this means that actually we can detect all the abnormalities, and with some false positive, of course. So if you compare it to what is done in the clinic now, you could say if you run this algorithm, you can get rid of pretty much half of the cases because they are non-informative. Of course, it's not the totality of the non-informative, but you do detect all the tumors, so you don't miss any cancer, and you do have here some false positives. Actually, about what you get, half are false positive, more or less, because of this false positive rate. But so this would be a first way which you could think about deploying the system and do a pre-reading, and then maybe decide if you want to assign the case to maybe a more specialized pathologist, or more like, general pathologists that may be less specialized on gastrointestinal applications. So, I mean, you can think about many ways of using this, but this was essentially the technical tool that we developed, and then based on the results, we can decide what to do next. Of course, this was validated only on internal cases, and it would need broader and multicentric and external validation to be more sure about the generalizability of the performance. But that was the first step. Still, when we talked with the pathologist, they said, okay, nice, yeah, you can pre-screen, but this doesn't really help me, because anyways, I have to still, write the report and close the diagnosis of this case. Can you help me there? Especially if you look at all these GPT-like models, large language models, a lot of text generated. Can you generate the report for me? So we can't yet, but we gave it a try with, kind of pilot study. And we said, okay, let's put all these polyps together, because you get multiple polyps from a patient. So we came up with we call it a packing of a slide. So we put all these fragments of tissue together, and the diagnosis of the patient is somewhere there in one of these fragments. We developed an AI, which is based on the CLIP model, based on contrastive learning, is multimodal vision and language. I'm not sure if you have covered that. We can discuss it later if you like. The idea is that from a single slide, you can generate a piece of text, right? Just predicting it from the pixel. And we didn't generate the full report. It was more like the conclusion, just a small part, let's say a caption, essentially. You can see it as a caption generation. And this was really a pilot study that we did in the context of a European project together with SURF, which is the HPC in the Netherlands. Here are just 3 examples that I want to show you. I don't get into the details, but I highlighted the key terminology here. And this is what the system predicted. Of course, it's much shorter, and it's not completely correct, but mostly the key terms are somehow there, except here where it just hallucinates adenocarcinoma. And actually, this was not a cancer case, because adenoma is like pre-cancer, or it's not an aggressive form of cancer, of tumor. And here, at some point, the system just went crazy and started spitting out nonsense, which happens. Of course, it was a prototype for us, but it was the first evidence that actually, okay, we can generate a piece of text from just the raw pixels, and it's promising for keeping investigating that, and maybe in the future being able to generate even parts of the report. All right, so then let's say that now we have the slide, it goes to the pathologist, right? And then they have to do their diagnosis. Okay, so what type of diagnosis? Okay, back to the example of our breast cancer grading. I take now the third component, the mitotic count, right? I told you that pathologists have to look for the hotspot where the highest density of mitosis is. The mitosis is the proliferating tumor cell. They look a bit like this. And we said, okay, let's develop an algorithm to detect these mitosis on the entire slide. Because if we have that, then you know where they are, you know how many they are, and you can also compute the hotspot. And maybe we can help pathologists with that. Actually, this is a pretty old algorithm we developed in 2018. We are retraining it now with more data and more modern technology and tricks, let's say, but we are still using it for many studies because it still works very well. So we said, okay, if we have this detection, we can actually pre-read the slide before it gets to the pathologist, and we can compute some form of density of this mitosis, right? Because if they have to look for the hotspot, and we know that they don't agree on where the hotspot is, because you can imagine they have to look on this slide. It's a huge slide. They can, stop at some point and say, okay, this, in my opinion, this is the hotspot. And another pathologist said, I think this is the hotspot. And they may be both right, because we did compute this density. And in this case, probably you agree with me, this is probably the hotspot. But actually, there are more hotspots, right? And then pathologists may just end up in one of them, and then they count mitosis there. So first, they don't agree on where the hotspot is, and second, if you show the hotspot, they also don't agree on what is a mitosis and what not. So we said at some point, can this be helpful? So what if we show the hotspot to pathologists? So we did a study with was again a small study with 2 pathologists and 90 breast cancer cases. And we measured the agreement on scoring, actually doing grading based on mitosis with and without AI. And we measured the kappa, so kappa is a metric of agreement without AI. And it was pretty much in line with what we saw in the literature. And then we gave the AI to both pathologists. Essentially, we showed the hotspot, and we saw that the agreement increased, which was expected because, of course, you pointed them to exactly the same location. So you get rid of one of the 2 variables for inter-observer variability, right? So you just say, okay, this is the hotspot, now count the mitosis. So still, it's not perfect. It means that they still don't agree on what is a mitosis and what not, but at least it improved the agreement regarding this aspect. So that was, again, something that for us in terms of diagnosis and breast cancer grading was the first evidence that, okay, we can use these type of algorithms to improve the reproducibility and therefore eventually also improve the diagnosis. So this was just, I mean, we can have more examples, but I think in the interest of time, I just, use this one because I wanted to cover also the last part, which is about treatment. So let's say we have the slide, the pathologist gets it, there is a diagnosis, it's cancer, and we know it's an aggressive form of cancer, for example, triple negative. Next question is, should we give neoadjuvant chemotherapy to this patient, or should we go for something else? And at the moment, as I showed you, they all get a neoadjuvant chemotherapy. So the idea here would be that at some point you still use AI to get this biopsy and, for example, predict before you give the treatment if the patient will respond to the treatment. Because if you know that it doesn't, then you just go to surgery right away, or maybe you use other types of treatment that are not the standard neoadjuvant chemotherapy, right? So this is, again, the same slide that I showed before. We developed a number of algorithms to actually encode a number of what we call computational biomarkers. So we looked into, for example, the presence of immune cells in the tumor area. We looked at actually the predicted value or the presence of proliferating tumor cells, so the mitosis also, which was not investigated in the context of predicting neoadjuvant chemotherapy response. We looked at a number of other morphological biomarkers, all done with AI, and we tested all of them in an external cohort. And these are the ROC curves that we got. You see, these are not super spectacular, let's say, but these are promising. They are all more or less above the diagonal that I mentioned earlier. And actually, if you take as an example like this, the red one here is CTILS, is the computational tumor infiltrating lymphocytes, so the presence of immune cells in the tumor, which of course immune cells should kill tumor cells. I will get back to this in a minute. Then we get something like this, right? We get 100% sensitivity at still quite high false positive rate, more than 60%. But actually, if you look at how this is happening in the clinic today, and you know that pretty much all patients are treated and only half of them get benefit, if you use this as a biomarker, what you get is that all the responders are detected because we get 100% sensitivity. Because here we were predicting responders versus no responders, right? So we take this score and then we use it as a selection criteria for the patients. So we find all the responders, so we treat all of them. And we also treat about 60% of the non-responders. So we over-treat them. But compared to what is happening in the clinic, we are actually sparing chemotherapy to about 40% of the non-responders. So it will be already potentially an improvement compared to what is currently happening in the clinic today. Of course, this needs to be improved. So we want the curve to be here, and all these no responders should not be treated, but they should get a different type of treatment. But this was again like one first evidence for us that where we saw, okay, yeah, that's a promising predicted value in these computational biomarkers, and it's worth further investigating that. So now we are looking to more more of these biomarkers, not only this ones, but also we are looking into ways about learning these biomarkers directly from raw data without having to, formulate ourselves like tumor infiltrated lymphocytes or this type of biomarkers that are anyway known from the literature. But yeah, this is still ongoing research that I don't have much to present here today. So maybe if you invite me again next time, I can present more. How about that? I would like to mention one last thing. I don't know how we're going time-wise, Luigi. Few minutes.
Well, just don't worry. Continue.
Okay, yeah. So one last thing, which sounds a bit like out of topic. You probably all know Netflix, right? I mean, nowadays it's a popular streaming service. But maybe you don't know that back in 2009, they were renting DVDs. There was no streaming. They were shipping DVDs. This is, I found it on the internet, Netflix in 2009, free DVD shipping both ways, right? So you can have a subscription and you were getting these DVDs. And of course, as they do today, back then they were already interested in predicting the ratings of movies of user, because they wanted to, know what movies you would have liked, right? To, customize a bit the advertisements, etc. So they decided to make a public competition that is called the Netflix Prize. They release 100 million movie ratings. So they release publicly a training set. And then they ask essentially the scientific community, but also industry. They only had some requirements. You should not be working at Netflix, or you should not be connected to Netflix somehow, but otherwise you could participate. And there was a $1 million prize for the winners if they could predict user ratings better than the Netflix baseline algorithm. So they had spent time and investments in building Cinema Match that could predict, the rating of movies given a certain user. If they could do 10% better than Cinema Match, then they could earn $1 million in prize. So they had this challenge, and actually there was a team that won. The Belcourse Pragmatic Cows. They managed to improve by 10.06%. So they got the prize. What is the message here, and why do I bring up this topic here in the context of medical imaging? Well, this was kind of collaborative research project, if you like, where you spend time. So Netflix had spent time on building their baseline algorithm. I don't know how much money, I don't know how many people, but they had some results, and they thought it could be improved. And instead of putting more money and more people and more effort themselves, they said, okay, let's make it open to the community. And then there are some clever people out there that can take our data. If we give enough data, enough high quality data, that they can develop their model, they can help us. And that's what they did. So actually, this is a concept of grant challenges that is also happening in medical imaging and in also many other fields. You're probably familiar with the platform Kaggle. In our group, we have developed a similar platform that is called grantchallenge.org that is only for medical image analysis challenges. And if you remember the example that I mentioned before about the first case where we show that AI can outperform pathologists on the detection of breast cancer metastases in sentinel lymph nodes, that was the result of a grand challenge that was called the Chameleon 16 Challenge that we held in 2016. And the solutions that you saw in these ROC curves actually come from a leaderboard of methods that we didn't develop in our group. The winning method was developed at Harvard, but then you see we had participants from all around the world: China, Germany, etc., both industry and academia. And the setup was very similar to the Netflix Prize. So we made a public competition. We shared 400 annotated pathology slides, so really these huge slides with exhaustive annotations. People had to predict the presence of metastases in lymph nodes, and there was no monetary prize at the time, right? But actually, the result was quite impressive, because these people actually managed to train algorithms that could outperform pathologists at this task. So this was in 2016, and we did it on the at that point we didn't use the Grand Challenge platform for evaluating this algorithm. Well, actually, people had to submit their results, and those were evaluated. Over the years, this Grand Challenge platform has evolved, and now you can actually submit your algorithms that you can do on Kaggle, and then the platform runs your algorithm for you on a hidden test set. So it's really an unbiased evaluation. And this is a mechanism that we used recently in another challenge that I organized together with colleagues, which is called the Tiger Challenge. And this was about, you remember this tumor-infiltrated lymphocyte that I talked about in the context of breast cancer? It's still a bit unclear how you can quantify these TILs with AI, and what is the predictive and prognostic value, if you can do it on biopsies, if you can do it on surgical resections, and what is the effect of this. So why are these TILs important? This is a video I found where these small cells here are the T cells, so the immune cells that are attacking tumor cells. And you see they actually detect the presence of tumor cells, and then they approach it and they start kicking it quite hard until you see in the end that they defeat it. But not all the T cells, not all the TILs can actually do that. And it's actually a question, what is the morphological background and the features in the tissue, in the tumor, in the connective tissue, in the immune cells? What is the formula that actually indicates that the TILs can win, let's say, and that actually treating a patient with, for example, immunotherapy or chemotherapy can be the right combination? So this is still an open question. And therefore, we organized this challenge, and it was, again, the same setup, a public competition. We asked people to quantify the lymphocyte in pathology slides. We also measured the prognostic value, so how this TILs, the quantification of these TILs would correlate with survival or relapse of cancer in these breast cancer patients. In this case, we did provide a baseline here. Bart van Rijthoven was a PhD candidate in my group that provided this baseline, and people had to do better than our baseline. Otherwise, they were not in the money, let's say. And there was a small total prize, not in cash, but because this challenge was sponsored by Amazon AWS, then they provided AWS credits as prize. And we had $13,000 in total, not for a single winner, but these were distributed across the top 3 of 2 phases. So it was a few thousands of dollars in credits for each winner in the top 3. So again, this was very similar in the settings like the Netflix prize, and it is actually a very powerful tool to disseminate and actually make the scientific community aware of a problem, especially in the clinical and the medical domain. Have collaborative efforts in trying to crack this problem in a few months, because these challenges typically run for 2, 3, 6 months max. And usually then the results that you get are better than the baseline results that maybe your team has been working on for a few years. So most of the solutions that I presented today are made by individual researchers or teams of researchers in my group, or in collaboration with partners. And of course, you can achieve a lot there in a multidisciplinary setting, etc. But when you make it publicly available and you open it to the scientific community, usually you can achieve even more. And then you typically boost innovation and research in a specific field. And you also make the community aware of this, medical problems and questions in diagnostic, for example, or treatment planning, etc. So I think we are a bit out of time, but I would like to conclude by summarizing these few points. I hope I convinced you or showed some evidence that AI can be used to address several tasks in medical image analysis. It can potentially support diagnostic and treatment planning and improve, ideally, the quality of healthcare and reduce cost. To do it, actually, we need large-scale, high-quality, annotated data to train, if we don't get into the realm of self-supervision. But let's say if you want to stick to supervised learning, high-quality data you need anyways. The annotations we can talk, but typically still needed. And then if you think about challenges as a collaborative tool to advance research in multiple fields, I hope I showed you that actually it is a very powerful tool. And it is also quite a lot of work, I can tell you, to set up and organize a challenge, but it's also a lot of fun. So I think that's it. I would like to conclude by acknowledging and thanking my group, the Computational Pathology Group, which, as I said in the beginning, has actually all the people that did all this work, which I had the pleasure to present to you today. And I would like to thank you for your attention.
So let's virtually give a big clap to Francesco. And we open the floor now to questions. Please don't be shy. Go ahead. No question.
Was very clear then.
Please don't be shy. Go ahead. Any question you may have, not just technical, but also curiosity. Well, if there is no question, let me also wrap up this lecture. You may have seen that the field here is really interesting. You may have understood that for doing a good job in a specific field, you also need to acquire quite some domain knowledge about the problem. Francesco said that all these terms he acquired during his career as a computer scientist, not as a doctor. Then he needed to really acquire this through the interaction with domain specialists. And this is important because you as a scientist in Francesco's case, but also as a data scientist, as a developer of AI system, you need to really understand, make sense of the results that you're making. If we go to the world of generative AI, you need to understand if your model is hallucinating or not, right? So and I think that the conclusion that Francesco said are very important, and I would like to really underline them. First of all, use technology for helping doing the job better and faster, right? It's not a replacement. Yesterday, actually, I was talking with a GP, a doctor that was running an ambulatory, and he said that, but for me, all this imagining things, robots doing surgeries, it does not help. I want an AI that will help me run faster my medical appointments and write medicines. This is the help that people need, right, to do the job better and faster. And this is also the message from Francesco's presentation. Help doctors, help even technicians to do their job better and faster with the help of technology. Second, technology is a way to make people agree. We have seen several examples from Francesco where doctors don't agree. I mean, we humans make mistakes. We are even not sure about what we are saying sometimes. And that's why sometimes we have a cabinet of medical councils that, they gather together, they find the proper decision in their diagnosis in this case. But with the help of technology, what we can have is actually even a better support to our decision. And this will make people agree better and even find better treatment, a better solution to move forward in saving life of people at the end. And this is what we are talking about today. And finally, last not least, what we have seen that, well, open up your problem to other people. That will bring new ideas, new knowledge, new way of seeing the problem. And this is especially also for yourself, because you come from different backgrounds, and this is where you will find your added value when you will start working in the technological field. And before closing, I see that there is Marco with hand raised. Please go ahead, Marco.
This question I should have done since
Go ahead.
Sale told that I always make questions. I wanted to say that the presentation was really interesting and actually explained clear, because not having any business knowledge about the medical sector, I could basically follow anything. So there's no question on that, more of a curiosity about challenges, since that Kaggle challenges are nowadays a norm and are getting very popular. So how was it working on a challenge? Because I asked that also in, let's say, as an opportunity that may also happen in our cases in other fields. I mean, you find yourself with a question to solve, and basically you need to start somewhere, and you want to get an higher score as possible on the metrics that the challenge is asking you to conduct your project. So how did you experience that, you and your team? How did you start gathering data from? I mean, in this case, you already had data, but how did you face it? And at the end, how did you feel even getting, I don't know, in the position that you got? Because even if you don't reach first place, it's always a good, I mean, it's still, you get satisfaction from reaching one of the first places. Thank you.
Yeah. Oh yeah, thanks for your comments on my presentation. And yeah, I think it's a good question about challenges. So I can tell you about my experience from the side of the organizing team, let's say, and maybe I can guess a bit of the position of a participant, what that could be. So as organizers, I think it's very important. So I agree with you when you say, okay, where do you start, right? So you have to think about being a participant. You're given these huge pathology images, but actually I think this holds for many challenges, right? So sometimes you're curious about the application and you have the technical expertise, but you don't have the domain expertise, right? So first is what do I have to look for? What type of image format is that? What is the actual question that they are asking me, right? Do I have to detect some objects or segment something? But what does it mean? How do I find also visually when I inspect the result if I have a false positive or not, if this makes any sense, if I don't have clinicians around me, right? So it's always difficult to make everybody in the position of understanding and working in the best possible conditions here. What we did was we provide as many tools as possible to get started. So the baseline that I showed in the leaderboard, we made publicly available under a permissive license. So with the training code, the training data, all the routines were all publicly available. It's all Python code, pretty, I would say, nicely documented. Maybe some participants didn't find it well documented, but I think it was all reproducible. We made examples also on how to they make their solution into a package. We use Docker containers to actually submit it to the Grand Challenge platform. So people could, from day one, they could, even without understanding what was happening under the hood, they could just reproduce everything from loading the data, so downloading the data, loading the data, training the algorithm, packing the algorithm, submitting it to the platform. So actually, we did see a lot of replicas of the baseline results in the first days because everybody was just doing some sanity check and rerunning the baseline solution. So while doing that, then at least the technical part was more or less covered. We provided information on the website with also videos that we pre-recorded about the domain, the domain, the problem, the clinical domain, what we were expecting from them, what we were looking for. Of course, we couldn't have a daily interaction with the participants, and maybe some of them had clinicians in their network that they could consult, but otherwise, yeah, they were just doing development themselves. We organized a couple of webinars during the challenge to provide feedback, to collect questions, and there was a resident pathologist from our group also involved in the webinar, so to address this type of questions. We had a forum where they could ask all sorts of questions that we were actively replying to. So all of this shows that it is a lot of work. Right, for a few, the preparation phase took us about a year. Then running the challenge was a few months, and then you see that ended in summer 22, and we're still finalizing the paper now. So it also takes a lot of post-challenge analysis. From the perspective of a participant, I think, yeah, it is also a lot of work. I guess it's also a lot of fun because then we saw that most participants actually made teams. Mostly within their research group. Also, a lot of companies participated. And for them is a way to actually showcase that they are capable of building good models. So for companies, I can imagine it's interesting to be in the top whatever in the leaderboard. For academics, it's important for their research to try out some novel solutions that they have come up with. I don't know, a novel way of training a segmentation model. Then if you can say, it got, I don't know, whatever position on the Tiger Challenge, then it's also a good way to advertise your results. They are part of a collaborative research project, essentially. So from the start, we said that essentially the paper we are working on now, there will be many co-authors that come from all the participating teams. at least the ones that made it to the final phases of the challenge. So it's also a way to engage with colleagues in the community that are working on the same problems as you. During these webinars, there was a bit of discussion. In the forum, there was discussion. So it's a research experiment in the end. And yeah, so I would say that it's from the participants' perspective, can be attractive in that sense. It can be some work. So also, if you're working on your PhD or in a company you're working on your project, I guess you have to discuss with your supervisors or your bosses that you do spend some time on. If you want to do it properly, you do have to, do a lot of experiments for a few months and really be on top of the challenge. But it could be an investment both for academics and industry. And for the organizers, it's a way, as I said in my presentation, it's a way to open up this clinical question with the research community to get a boost in the field for that specific application, and that's what we want, right? We want to move this forward and improve healthcare. And then if at some point we reach a limit or we have to invest more internally with more grant applications or more fundings, whatever, if you open it up and then you can make the next step with the community, I think that's a very valid reason. But it is a lot of work, I can tell you. So I wouldn't do like challenge organizer as a full-time job if you have a position as a researcher. But organizing challenges it's a very powerful tool.
So thank you, Francesco. Any other burning question? Yes, Flavio.
Yeah, sorry. Was about let's say the diagnostic and the fact that with let's say using AI as a copilot somehow, the agreement between the diagnostic, let's say was increased.
Mm-hmm.
At which level is let's say is used let's say the AI in that case? What I mean is that I don't know, you are which is the policy? I mean, the system, the model is giving some feedback regarding, I don't know, in that area you have some tubular cells, or there is more goes more in details, so it already starts with the diagnosis. Just to understand. Yeah, sorry.
No, sorry. Please go ahead.
I hope it was clear, but
yeah.
I was.
Yeah, no, sure. Yeah, I just want to make sure that you ended your question. Yeah, I think it was clear that. So if I understand correctly, the question is, okay, I show that, for example, for the case of mitotic figures, you can provide some visual feedback to the pathologist. The question is that all you show, or does the system actually perform the full diagnosis under the hood, and then how do pathologists interact with the system? Do they have to just check and sign off, or it's more and they get this visual feedback and then they take it from there and then they do the mitotic count themselves and then the rest of diagnosis themselves? I guess I think I understood this was the question. If that is the case, then
yes.
The answer is I don't have a concrete answer for this, because so what I showed is still, at least for us in our group, it's still at the research level. So we did that study to check actually if showing this visual feedback was reducing the inter-observer variability. So in that case was the hotspot. Then you can go further and also show the mitosis and maybe even more, some form of, confidence at cellular level, stuff like that. We didn't do that part yet. Actually, we are doing it, but it's not, the study is not finalized and it's not published yet. When it comes to actually using it in the clinic, there are a few solutions for mitotic count at the moment that will be on the market or are on the market since recently. But I'm not aware of, a standard protocol where you say you have to use this algorithm, this is the feedback that it gives, and then this goes into the diagnosis. I think it's still to be defined. Also because it's good to realize that, especially for pathology, this is still, in a way, it's still in its infancy. So pathology is digital since a few years, And the AI development is also happening in the past 8 to 10 years. But going from the lab to commercial solutions really takes a lot of time. And then you have to enter, the regulatory part, certification of products. So I think there are studies on, people do like vignette or user studies, usability studies with visual perception and stuff. So there is a lot of research happening, but there is no single specific ways of using these algorithms. If it's more at the visual feedback or just providing the score for cancer, or going all the way down to the report. I think it depends. So I think time will say what is the best way of using this algorithm. I think the first step is to make sure that they are accurate, that they work very well, that they are robust, that what they find in data that come from one hospital also holds for another hospital. And still there is research there because it's not really fully there yet. And then we'll start with the usability and the interaction with the clinicians and so on and so forth.
Yes, Angelo.
Hello, everyone. Thanks for the lesson. My question is about the I think the last study you showed us on biomarkers. I was just curiosity. I was just wondering, how do you coordinate your work with the molecular department if you ask to confirm your data? And I don't know if you think that to predict biomarker, it would be more effective to use some sort of multimodal approach, or you just relying on images? Thank you.
Yeah, excellent question. So the answer to the last part is yes, we should go multimodal. And it's something that we are also working on. The problem with multimodal is that you need high quality data from a sufficiently large number of samples or patients with all the modalities in place. So the more modalities you add, the more your numbers go down, because then you lack some modalities. Then you enter the space of building models that can deal with missing modalities. That's always a question, but it's an active research aspect. So why didn't I show things on multimodal? Well, simply because the first applications and the first results we got are on histology only, and that's where we have the bulk of data that we use to train and validate the algorithms. I always say that the future, actually the present, is multimodal. So indeed, molecular data, genetic data, even combination with radiology data is the right way to go. I mean, there are more and more biomarkers, liquid biopsies. For lung cancer, for example, there is the eNose technology that actually analyzes the breath of patients and stuff like that. So eventually, I would like to see that all these biomarkers and all these modalities come together. We start with pathology because that's what we do, and also that's where we have, as I said, the largest amount of training and validation data. For the data we used, so the molecular subtype was confirmed by tests done in the lab, and that is done in routine diagnostics. So when there is a breast cancer case, then they do molecular tests to classify it as it's called ER, PR, HER2, or triple negative. So these tests are done. If it's negative to the 3, then it's triple negative. Ideally, you want to do it with molecular tests, but in practice, it's done with a technique called immunohistochemistry. So it's done in the pathology lab with staining and targeting these cells with antibodies. But anyway, you can get this information from the lab, and it's pretty reliable. So that's how we identified the triple negative cases compared to the rest. And about the response to the treatment, that we don't need to get from the lab. That actually comes from the surgery, because in this neoadjuvant chemotherapy setting, as I said, the patients get the treatment and then they all get resection. And then the resected tumor is, if the treatment has worked, actually the tumor shrinks, so it's much smaller. And that's also good for patients because maybe they don't have to get mastectomy, so the breast removal surgery, but they can get much less invasive surgery. And then typically they also do better in terms of survival. But in any case, you do have the resected tumor, which goes to the pathology lab, and then pathologists check for the presence of tumor cells. So if the treatment has worked perfectly, in principle, there are no tumor cells left. And that's our gold standard for saying the patient has responded. Then there are, of course, there are also classification systems to say if it's complete response, if it's partial response, if it's complete response, near complete response, partial response, or no response. That's one of the classification system called RCB that I can think about now, but there are more than that. So you can use that as your gold standard to train your algorithm and say what type of response you can predict. Ideally, you would like the it's called PCR, pathological complete response, but you can also target, for example, near complete response, because that might also have some clinical benefit. So all this information we get after surgery from the analysis of the histology sample in the pathology lab. But the initial classification we do with immunohistochemistry. I'm not sure if this answers your question entirely.
Yes, thank you. I just wanted to make a question because I thought we can have the reverse approach. I mean, we can start from the molecular approach and then go back to images. So that's why I asked about multimodal. And yes, and it's a promising field, I'm sure. I'm sure also you have a big archive with slides and you can do a lot of retrospective studies and integrate and with new data too. Thank you.
Yeah, but there is also another aspect that is, so histology is always there. Actually, it is a very old field, and it's also relatively cheap these days. So especially these H&E slides, so the pink and blue that I've shown, making those costs not a lot, in the order of a few euros, and it's much cheaper than genetic and molecular tests that might provide complementary information, but they may also give the same information that one can learn from the analysis of the tissue morphology from H&E slides, for example. So there are many studies actually trying to predict also molecular status and genetic mutations from H&E slides. And actually what I've seen from publication, it seems that at least the quantitative performance are promising. Of course, not at the level that we can already use in the clinic as a replacement of molecular and genetic test. But I think the idea is to use those more like a pre-screening or pre-selection case. Also because these tests are very expensive, right? This genetic test. And if you know that upfront that some will be negative or maybe positive, depend on how you train your algorithm, then you can use these models to do some form of pre-selection and therefore, speed up the test and then reduce costs, etc. So there is also a way to use this information as a target and then start from the histology, but use the molecular test, the output of molecular test as an endpoint, let's say. Here we just follow a different approach because we were more interested in looking into the morphological characteristics of, for example, immune cells. But other approaches are possible, of course. No more questions?
No more question? So then let's thanks again, Francesco. Big clap and a big thank for being here with us. And also for a late lunch in Netherlands, because in Netherlands lunch is much earlier than here than for us, let's say. And thanks again, Francesco, and thanks again for the people watching the live stream in YouTube, and for the students. We will see each other Friday at 6 regular time for course on ethics and regulations. Bye bye. See you on Friday.
Thank you. Bye. Have a good day.
Thank you. Bye bye.
Bye. Thank you.